Very good morning to everyone. My second module on VLSI design challenges and solution. So today we are going to discuss about the uh, VLSI major constraints, what actually the designer facing during the fabrication of the chip, and how we can solve the problem related with the VLSI design. So go with this outlines. The first is challenges in the VLSI design, contribution of the power dissipation, leakage flow, research opportunity, VLSI design flow, references. So the first one is the introduction part where the VLSI is a very large scale of integrated circuits. When a single chip having millions of transistor connected on it, it comes under this scaling technology that is called VLSI, very large scale of integration. And the major constraints of any VLSI chip is always its size or area, power dissipation, its speed or clock speed, and fourth one is design time. So among all these four constraints, the power dissipation becoming the major constraints due to all the battery operated devices or portable devices. And the solution is to go for a low power VLSI design, which makes available extended battery life and enhance the performance. So we want our portable device or our mobile phone or any portable gadget to perform the same speed and the same criteria as our desktop computer gives. So these all the criteria will fulfill on the cost of power. So the power dissipation or the battery life degrades fastly. So the solution is to go for a low power VLSI design. Means our chip size is smaller. So due to this small size of chip, we can use a least power as compared to the earlier higher size chip. And the if we reduce the power, the in the same time we also reduce the threshold voltage of the device. So as we reduce the threshold voltage, we fast our device as well as the performance, but various parameter or the factors which are proportional with the threshold voltage comes in the picture in this VLSI design flow. So what are the problems or what are the challenges with this low power VLSI design phase, and what are the solution we will see in our next slide. So basically, the as we talk that power dissipation is the major concern in our nano scale devices. So these are some fact. This graph is taken from ITRS International Technology Roadmap for Semiconductor, and it is shown two power dissipation. One is static, another is dynamic power. So the static power dissipation means when our device is in idle mode, means there is no clock frequency uh, continue at all. And the second one is dynamic power dissipation, means when the device performing some task like playing some music, talking with the mobile phone, playing some movie, or the person working with this with their gadget. So during this dynamic mode, this red color line is shows clearly. In the earlier days, when in 1995 to 2000 and 2005, this red color line which shows the dynamic power dissipation is more dominating over the static power dissipation. We also say leakage power uh, is the another name of static power dissipation, and which is dominating over this. The dynamic power is dominating over this leakage power uh, till 90 nanometer technology. The technology is represents the drain to source difference between drain to source distance of any transistor. So as the technology scales down, the criteria will change. So here we see after this 690 nanometer technology, the static power dissipation becoming the more dominating over this dynamic power dissipation. It means that when our device is in idle mode, or if we see the complete system which is in idle mode, the power is dissipated more than 50% in this case. So due to this leakage power or static power dissipation, our battery will be completely drained out. So this is the major contributor in DSM technology, that is deep submicron technology. Beyond this 65 nanometer technology, we say DSM. So in this graph, the x-axis, bottom x-axis represents the year, and the top x-axis represents the technology of the transistor, and the left of the y-axis shows the normalized power. So this is the graph between power dissipation and year of invention. Now we start with what actually the dynamic power dissipation is. The dynamic power dissipation is basically also known as switching power dissipation. When our device perform all the switching activity, uh, like working with our gadgets and playing some music or some videos, or talking with the phone. These are some activity when our clock frequency will be active. In this mode, the power will be dissipated is known as dynamic power or switching power dissipation. So this power dissipation is basically proportional with the frequency, capacitance, and the square of the supply voltage, that is FCV square. So this is the power dissipation curve between here and the power given in the watt. So Intel 4004 processor, it was the first processor made by Intel in 1971, and this keep the power is keep on going till Pentium 4 processor invented in 1992. So this is the graph. This graph shows the exponentially increasing of power dissipation or dynamic power dissipation of a processor. Now, what we do to reduce this dynamic power dissipation, this flow shows the uh, things regarding low power dissipation designs. So this in this flow, very first is transistor size scaling. So according to the Moore's law, actually in VLSI industry, the Moore's law is very famous, which who told about the performance and other criteria, in which once we uh, if any electronic industry wants to grow in a future, they adopt the formula that is in every 18 months, the size of the uh, transistor will get half. Means if the number of transistor is double in every 18 to 24 months, the performance of the chip is increases, and it is beneficial for any electronics or semiconductor industry. This law is given by the Morse in 1965. So as the transistor size is scaling, we directly increase the density of the transistor, means the number of transistor per unit area of the chip is increases, and at the same time we also increase the operating frequency because we want faster device in the future. So we cannot control the frequency and the size, which increases the power density. All the things increase in the dynamic power dissipation due to the proportionality of FCV square. So the solution, what is the solution? The solution is low power design. So this low power design means low supply voltage. The supply voltage of the chip will be reduced. And to maintain the performance means once we suppose we are working on 10-volt IC, and at the same time we also working on the 2-volt IC. So the 10-volt IC and 2-volt IC having different current carrying capability. So due to this carrying capability, the speed will be degraded on the low supply voltage. So to maintain this particular performance, we also reduce the reduce the threshold voltage of the device. If we reduce the threshold voltage of the device in the same manner, we maintain the performance of the chip at the lower voltage also. But what is the cost the designer will pay? The low threshold voltage means the I sub threshold current or the leakage current. This leakage current is basically proportional with the mu, is shown in this equation, that is this is mu w c ox by l v square e to the power vgs minus vt upon eta vt 1 minus e to the power minus vds upon vt. So this leakage current is proportional to the mobility of the current charge carriers. W is the width of the device, means width of the transistor. Length of the channel means L is the length of the channel between drain to source distance. C ox is the oxide capacitance. VT is VT square is the thermal voltage or the voltage temperature dependent voltage, which is 26 millivolt at room temperature. And e to the power vgs minus vth upon eta vt, it means that the gate to source voltage is vgs, threshold voltage of the device is vth, and eta vt, where eta is the proportionality constant. It depends on the long channel and short channel device. And vt is the thermal voltage. 1 minus e to the power minus vds upon vt, here vds is again a drain to source voltage. This equation basically represents the all the terminal voltage of a single transistor, which is exponentially proportional to this leakage current. So once we reduce this threshold voltage, we also reduce all the gate, source, and drain terminal voltage, which will increases this leakage current. And this was not the case in earlier devices because we work on the higher supply voltage. But as we reduce the low supply, the threshold voltage will low and all the terminal voltage will be reduces in the same manner. So they will increase the sub threshold current or leakage current of the device. This will shows the scenario as we seen in the ITRS curve, where after 90 nanometer the leakage current becoming the more dominating over the dynamic power dissipation due to this reason. So the outcome of this is high leakage current. So this is the transistor leakage mechanism. So so I think we should close this topic today. And in our third module, we start with the leakage mechanism, and we see the various kind of leakage current and how we can remove all these leakage. Thank you so much.